So if momentum is conserved and I just added more mass, see how this would now go slower? So you can think of it as like mv is now 3m. So if this was my original v, so my new velocity is 1/3 of my new velocity is 1/3 of my old velocity. But you don't need to do the math. All you need to say is, okay, this is a collision, momentum is conserved, so now it's going slow. So in the collision, total momentum is conserved. So the blocks are moving slower now than originally. Okay, now what does moving slower have to do with the how far it's going to be compressed? So if there wasn't a collision, we would say energy, this is conservation of energy, right? So my potential here, all potential, would be going to all kinetic at the compression and the stretch date point. So I put all potential. It's all kinetic here. It's going to all potential. Because here your x is 0, potential 0 means it's all kinetic. Here you have the most potential, so it's all potential there. Okay, so now I need to think, how did this affect my kinetic energy? Kinetic energy is 1/2 mv squared. Yes, I just got more mass, but see how I got less velocity? Velocity matters more, so overall I have less kinetic energy. So I'm moving slower now than originally. So there is less kinetic energy at equilibrium, which means I have less spring potential energy at the amplitudes. If spring potential energy is 1/2 kx squared, and this is less, and you still have the same spring, so the same spring constant, see how you have less displacement? So that'd be less x, which means less amplitude now. So my new amplitude is less, so APQ is less than the original. And another real doozy. Okay, so this is the experimental design from last year. We've got a large batch of conductive dough that conducts electricity. They mold it into cylinders with some areas and lengths. Each student applies a potential difference across the ends of the cylinder and determines the resistance. The results of their experiments are shown. So we've got the area, the length, the voltage, and the resistance of each dough cylinder. I want to calculate resistivity of the dough cylinders. I want to know what I would, I hope you didn't see that, grab the equation sheet. I want to know what I would need to plot in order to get resistivity. So this is where you go to your equation sheet and you're like, I know what resistance is, what's resistivity? Well, look at your equation sheet and you'll see right here, resistivity is this rho, this P right here. So make a note, resistivity. Again, not the same as R. This would be a terrible question if resistivity was resistance, because hey, here's resistance. So let's look at our equation sheet. You should look for the resistivity symbol, and then I see R equals resistivity L over A. So I want to get this. I have a graph. The easiest thing to do is think of this as like a y equals mx equation. If I want my slope to be the resistivity, so this is my m, then you want r to be your y and you want L over A to be your x. So what you want on your vertical axis, your y-axis, is just resistance. And what you want on your x-axis is the L divided by A. So now I want to plot these actually. So vertical is my resistance, this is resistance, and this is L over A, which is length over area, which it said didn't include units, so length was measured in meters, area was meters over meters squared, which you can simplify to 1 over meters, or you can just leave it, it doesn't matter. Oh, I should have left room for me to write my numbers, oh well. Alright, so now we want to actually plot scale and plot the points. So scaling means I need to look at how many numbers I need and scale to fit all of those on there. So So let's look at resistance first. I've got 20, 30, 60, and 100, and I've got 1, 2, 3, 4, 5 big ones. So I went by 25, 25, 50, 75, 100, and 125. I would use nice numbers. I'm sure I could have fit it a little bit nicer, but I would have had nasty numbers. Let's just use nice numbers. And then I have to at least use half the graph. So if you're not using, like if you had 100 right here, that you would not get points for like scaling properly because you need to use at least half of the axis. And then L over A. So first of all, I need to calculate what L over A is. So I went through each of these. This divided by this equals. This divided by this equals. And got what L over A equals for each one. So I got 61.22, 102, 150.9, 263. So I need to go to at least 260. 1, 2, 3, 4, 5, 6. This one I went by 50s. Be neater than me, because I forgot that I would need to do this. Alright, so 260 is using at least half my graph, so that's good. And now I plot. So this is my x-axis, and then this is like my y-axis. So at 61, I want 23. So go to 50, this is 60, so 61 is just over, and then just to 25 is right here. 102, so this is 100, and then I need to go to 30, which is right here, 31. 150 right here, going to 60, right here. 260, going to 105 right here. Right, I have 4 different dots. Now what we do not do is we do not just put the end in the middle. We're going to do like a line that has some above, some below. So maybe something like this. So see, I have 2 above the line and 2 below the line. That's good. And now I want to get an estimate for the resistivity. So remember, we made it so that it was y equals mx, where m is your resistivity. So resistivity is just my slope. Now I need to pick 2 points on my graph, not the plotted points, but points that mine went through. So this looks like a point right here, and like right here. So then I labeled, this was 240, 100, and this one was 102, so it was 35. And then slope is just change in y over change in x, which is change in y is 100 minus 35. Change in x is 240 minus 100, and then just get your, I had a different number when I made my key because I had slightly different points, so then just get this number. And that's your resistivity, or our estimated resistivity. Another group of students performs the experiment, but now they shape it into rectangular shapes instead. What will this do to, will this affect the resistivity? So what resistivity is similar to resistance, but resistivity is for a material specifically. So when you do it into a different shape, if you look at the equation, so the resistance matters on the resistivity of the material, and depends on the resistivity of the material and the shape it's made into. Is it like longer? Is it fatter with a greater cross-sectional area? But the actual resistivity of the material depends only on the material. So no, because resistivity depends on the material, not the shape. Whereas the actual resistance depends on the shape and the resistivity. Okay, we want to describe an experimental procedure to determine whether or not the resistivity depends on the temperature of the dough. So what you are, for sure, you're going to get a point for just knowing to change the temperature of the dough. So how would you change the temperature of the dough? So like a typical, like, oh my gosh, what's the word? Lab equipment to change temperature would be like a hot plate, right? So we're going to change the temperature, so I'm going to just making notes off to the side. Use a hot plate to increase the temperature. I want to actually measure the temperature, so measure using a thermometer, right? And then I for sure need to measure the resistance. So what I can do is I can apply a voltage, and you can measure it using a voltmeter, and then measure the current using an ammeter, and then you can use that like I equals V over R to get R. But I think they don't even ask you to analyze or ask how would you analyze it, so I don't think you need this, but like if you know your voltage, measure the I, use that to get your R, right? So I can then see the relationship between changing temperature and resistance. We need to be careful here that we're keeping everything else the same. So like let's just make it into one shape and use that same shape of dough, cylinder of dough the whole time. So I'm going to create a cylinder of dough and measure the length and area of the cylinder. For each trial, I'm going to use the same dough cylinder. This is so weird, such a weird experiment. Okay, now what we're going to actually change is for each trial, use the same dough cylinder and change the temperature of the dough by using a hot plate and a thermometer to measure the temperature of the dough. So I've changed like my X variable, and I know exactly how much, oh, that got shifted. I know exactly how much I've changed it because I'm measuring the temperature, and now I need to measure the resistance. So I'm going to apply a voltage across the dough and measure it with a voltmeter, and then measure the current through the dough with an ammeter. Use delta V and I to get the resistance. And then you'll be able to, it didn't ask for the analysis, so you don't need to put this, but you'll be able to make like a table with the temperatures and the resistances to see whether or not it depends on the temperature or not. Now typically, it didn't this year, but it typically asks you explain how you would analyze your results to see if this hypothesis is true or not. That's where you would say like, okay, make a table of your temperature and resistivity. If this, as temperature changes, this changes, then it depends. If it does not, then it does not depend, etc.